Alright, in this video we study relations. A relation is used to compare two elements in a set. You already know a bunch of relations. For example, for any numbers a and b, we may say that a is equal to b. So this equality is an example of relations. And that says two elements a and b are identical. So if they are identical, then we say they are equal. So this is a relation. And we may also say that A is less than B. That is also an example of relations. So we can generalize this idea to include other types of relations. And a special type of relations called equivalence relations is used for classifying elements in a set. Okay, so let's start. So we are going to consider many kinds of relations. So instead of writing like they are equal or less than or greater than or whatever, we can use any symbols to express relations. For example, any like a diamond relation or square relation or heart mark relation or whatever, like 3 bars, tilde, or let's say any symbol like alphabet relation R. So we can write A, R, B to express some kind of relation called R. Okay. So what we happen to know is something like A is equal to B. So in this case, that this R happens to be this equal sign. So we can use any symbols as long as we are clear about what we are talking about. So let's define a relation more formally. So what is a relation anyway, in general? So here's the definition. Okay, a relation, let's call it R. So a relation is always defined on a set. So a set must be given. On a set, say S is a subset of S times S. So this is a Cartesian product between S and S. Okay, so that is the relation. I mean, the definition of a relation. So that means since this is a Cartesian product, its elements are a pairs. So A, B, it's a pair if it is in a relation, so which is a subset of S times S. So A is an element of S and B is an element of S. Okay, so if this, then we write A is related to B by this relation R. Okay, so this is a special notation. R is a subset of this Cartesian product, but R is also used to represent the relation between elements A and B. Okay, so this is simply a shorthand notation for this. Okay, so relation is just a subset of a Cartesian product. Maybe this definition is a bit too abstract, so let's see an example. So you know the equality on natural numbers. Okay, so equality on the set of natural numbers. Okay, so this is a relation. So what kind of relation is it? So this equal sign is a relation. So by definition, this is a set of pairs where A and B are natural numbers and A is equal to B. Of course, we are now trying to define this relation, so maybe it's not a good idea to write like this. So instead of writing like this, we write like this. A and not B, but A. A and A. So we repeat the same element twice in a pair, and A is any element of natural number. Of course, this is a subset of the Cartesian product between the set of natural number with itself. Okay, so this is a subset, of course. So to be more explicit, this set is something like this: 1, 1, 2, 2, 3, 3, and so on. So we just have the same number twice in a pair. And this is obviously a subset of this, which is, to be explicit, it may be something like this: 1, 1, 1, 2, 1, 3, and so on. So this continues forever. And 2, 1, and 2, 2, and 2, 3, and so on. So there are many, many elements, infinitely many elements. But so this corresponds to this, and 2 corresponds to this, and so on. So only part of this Cartesian product are present in this relation. So we name this relation as this equality. So this is a subset. And if a pair belongs to this subset, then we write 1 is equal to 1, or 2 is equal to 2, and so on. Okay, let's see another example that is less than relation on the set of integers. So how do we define this? So this must be a subset of the Cartesian product of integers with itself. Okay, so this is a subset definition such that, so it's a set of pairs where each element is an integer such that A is less than B, right? But of course, we are not trying to define this less than symbol, so we shouldn't use this here. So how can we define less than relation without using less than? So this is ill-defined. So here's how we do. So A and B are integers, and such that there exists some natural number C such that A plus C is equal to B. So is that okay? So C is a natural number, so we assume that natural numbers are already defined. So that's fine. So natural numbers are always positive. So if we add this natural number to A, then we can make that sum equal to B. So we assume that this equality relation is already defined. So if this holds, then that means A is less than B. Okay? So if A, B belongs to this relation, then that means we write A less than B. Okay, so this is less than relation is a relation, and it's a subset. Okay, it's a subset of Z times C. All right, among various relations, there is a class of relations that is called equivalence relation. So let's define that. That is very useful and often appears in various places in mathematics. So let's define it. Let tilde be a relation. Relation on a set S. Okay. Then we say this is an equivalence relation. Relation so if the following conditions are satisfied, there are three conditions. First is called reflexivity. Reflexive. That is for all elements in S, for all element A in S, we have A is related to A itself. Okay. This seems trivial, but this doesn't hold for less than relation, for example. And second, it's symmetry. Symmetry. That is for all elements A and B in S, if A is related to B, then B is related to A. Okay? So if this is true, then this is true. So it's symmetric. If we swap A and B, then we still have the same relation. Okay, and three is called transitivity property. Transitivity. So that is for all A, B, C in S, if A is related to B and B is related to C, so then A is related to C. So that means if A is related to B and B is related to C, then A is related to C. Okay, so this is called transitive property. So if these three conditions are satisfied, reflexivity, symmetry, and transitivity, then we say this relation is an equivalence relation. That's the definition. And if this relation is an equivalence relation, when A is related to B, we say A is equivalent to B, or B is equivalent to A. Because of symmetry, it doesn't matter which one comes first. Okay, let's see a few examples. First of all, the equality on, for example, integers is an equivalence relation, right? So for any integer A, of course A is equal to A itself. And about symmetry, if for any integers A and B, if A is equal to B, then B is equal to A. This is obvious, right? And three is about transitivity. For any three integers A, B, C, if A is equal to B and B is equal to C, then of course A is equal to C. Therefore, this equality on integers is an equivalence relationship. And next example, we actually already explained that during the definition of equivalence relationship, but less than relationship. Less than relation on a set of integers, for example, is not an equivalence relation. First of all, for any integers a, we do not have a is less than a. This is wrong, right? This is false. Therefore, it is not, this relation is not an equivalence relation. What about other properties? So if a is less than b, is this true that b is less than a? No, of course not. So this doesn't hold either. So it's not symmetric. What about transitivity? If a is less than b and b is less than c, is that true that a is less than c? Yes, of course it is. So transitivity does hold, but other two properties, reflexivity and symmetry, they do not hold. So it is not an equivalence relation. And yet another example. Let's define this relation, this 3 bars on the set of integers. So for any integers a and b, we write a is related to b. So but this is definition. If and only if a minus b is divisible by 3. So we write 3 divides a minus b. So if this is true, then we write a is related to b. Let's show that this is actually an equivalence relation. Okay, this relation is also called congruency. So a is congruent to b. Congruent to b. Okay, modulus 3 in this case. 3. Okay, so let's show this is an equivalence relationship. And first of all, reflexivity. Let's say a is an integer. So a minus a is 0, which is a multiple of 3, right? So it is divisible by 3. Therefore, a is congruent to a itself. We sometimes write mod 3 here. And what about symmetry? So if a and b are integers, and we assume a is congruent to b. So this means, by definition, a minus b is some multiple of 3, where k is an integer, right? So that means if we multiply both sides by -1, then we have, let's write it step by step. -1 times a minus b is equal to -1 times 3 times k. Okay, k is any integer, some integer. So this becomes b minus a and 3 times -k, right? So b minus a is a multiple of 3. So for some k, right? Therefore, b is congruent to a. So symmetry does hold. If this is true, then this is true. Okay. So next, lastly, we need to show transitivity. So let's say a, b, c are integers, and we assume a is congruent to b and b is congruent to c. Now, if a is congruent to b, then a minus b is some multiple of 3. And b minus c is some multiple of 3. And k and l are some integers, right? So there must exist some integers k and l such that this and this hold. So a minus c, we want to show that a minus c is a multiple of 3. So a minus c, we add b and subtract b. So a minus b plus b. So we added b and subtracted b. So this is 0. So this is same as this. Okay, but a minus b is this. So 3k. Okay. And b minus c is this, 3l. So factorizing 3. And k plus l is of course an integer because k and l are both integers. Therefore, a is congruent to c. So transitivity does hold. We assume this, then from that, this was derived. So all three conditions are satisfied. Therefore, this congruency relation is an equivalence relation. By the way, what's the meaning of this congruency relation in this case? So a minus b is divisible by 3, or it's a multiple of 3. So, for example, 1 is congruent to 4 because 1 minus 4 is negative 3, so it's a multiple of 3. And 2 is congruent to what? For example, 5, or which is also congruent to, so 5 plus 3 is 8, and so on. Right? And what about 3? Of course, it is congruent to 0, and it's also congruent to 6, and congruent to 9, and so on. As you can see, this is a multiple of 3. And however, for example, 1 is not congruent to 3 because 3 minus 1 is 2, which is not a multiple of 3. And 2 is not congruent to 3 because 3 minus 2 is 1, which is not a multiple of 3. And actually, this is congruent to any number that has a remainder of 1 when divided by 3. So 1 is equal to 3 times 0 plus 1, and 4 is equal to 3 times 1 plus 1, and this is also congruent to 7, and 7 is equal to 3 times 2 plus 1. So everything that is congruent to 1 is equal to a number that has a remainder of 1 when divided by 3. And similar for this. So any number that is congruent to 2 can be expressed as a number that has a remainder of 2 when divided by 3. And this one, so any number that is congruent to 0 or 3, they are congruent to, they are multiple of 3. That is, they have remainder of 0 when divided by 3. Okay, and all integers belongs to either this class or this class or this class. So any integer can be divided into 3 classes. And also, it's important to note that these 3 classes do not overlap. They have no common elements. Okay, anything that belongs to this class do not belong to other classes, and same applies to other classes also. In other words, these 3 sets, okay, we can define 3 subsets of integers, and these 3 subsets do not have any common elements, so they are disjoint. Okay, they are disjoint with each other, and also together, if we take the union of these 3 subsets, then that union is equal to the set of integers, all of integers. Okay. This observation can be generalized to any equivalence relation, actually. So let's define some ideas. First, define the idea of partition over set. Over set. So let S be a set, and let's say C is a collection of subsets of S. It may not contain all the subsets, so it's not a power set. So it's just let C be just a collection of subsets. Then we say C is a partition of S is a partition of S if the following conditions are satisfied. There are three conditions. Then if X belongs to C, so X is a subset of S, then X is non-empty. So this collection C does not contain the empty set as its member. And two, if X and Y are elements of C, then they are disjoint. So their intersection X cap Y is empty. Okay, and three, and the union of all elements of C is equal to S itself. So let's say if there are n elements, x1, x2, and let's say maybe I should write this. C is equal to x1, x2. If there are n elements in C, then if we take the union of all these elements, x1 cup, x2 cup, and so on, cup xn, then this is equal to S itself. So sometimes this the number of the cardinality of C may be infinity. So in that case, we write like so instead of writing like this, we write union I from 1 to n, and xi is equal to S. Okay, so this is like writing like a sum symbol. Instead of writing like this, we write like this. Okay, it's like instead of writing like x1 plus x2 plus and so on plus xn, we write this sum symbol I from 1 to n xi. Right? It's similar. So the union of all elements of C. So each of these elements is a subset of S. So if we take the union, then the result is the set S itself. Okay. So if these three conditions are satisfied, we say C is a partition of S. So why do we call it a partition? Okay. So that means if we have a set S, then we partition this set into a collection of subsets, right? So let's say x1 is like this, and x2 is like this, x3, x4, and so on. Okay, so none of these subsets overlap with each other, with other subsets. Okay, and together, if we take the union of all these subsets, then we can recover the entire S. Okay, we say this property mutually disjoint. Disjoint. And we say that the third property, this property, collectively exhaustive. Okay. then uh, uh, in a sense, we are classifying the elements of S. So one class, another class, yet another class, and so on. So they do not overlap. So each element of S belongs to a distinct class of subsets of a partition. So how does this idea of partition relate to equivalence relation? Actually, if we have an equivalence relation, then we can derive a partition based on that equivalence relation. So let's see that. And that is, first we define an equivalence class. Okay, so let tilde be an equivalence relation. On some set, let's say on some set S. Then for each element in S, each element X in S, we define an equivalence class of X. Equivalence class, the equivalence class of X is defined by this bracket X, that is the set of elements Y, all elements Y, such that Y is equivalent to X. Now, of course, Y must be an element of S, right? Y is an element of S. Or maybe we can write so Y is an element of S such that which is equivalent to X. Okay. So X bracket is a subset that contains all elements of S that are equivalent to X. Okay, so this is called the equivalence class of X. In the previous example, we defined the congruence. A is congruent to B mod 3. So that is, if A minus B is a multiple of 3, then they are equivalent, right? So let's define an equivalence class of each integer based on this equivalence relation. Okay, so equivalence class of 1 is, what is it? So that is any integer such that Y is congruent to 1. So this is actually the set of all integers that are that have a remainder of 1 when divided by 3. So that is all integers such that there exists some integer k such that y is equal to 3k plus 1, right? So this is actually equal to 1, 4, 7. Actually, there are also negative numbers and so on. And for example, let's say, so 1 minus 3 is negative 2 and negative 5 and so on. So, and you can see that this is actually equal to the equivalence class of 4. It's the same thing. So this subset and this subset and this subset, they are the same subsets. And of course, as you can see, this is also equal to this bracket 7 and so on. And similarly, the equivalence class of 0 is all integers such that y minus 0 is a multiple of 3 for some for some integer k. Okay, so y is a multiple of 3, so this contains 0, 3, 6, actually plus minus, right? 9 and so on. And another equivalence class is this. So that is 2, 5, and 8, and so on. For negative numbers, we have -1 and -4, and so on. And let's write like this. Then that will be y. There is some integer k such that y is equal to 3k plus 2. So when divided by 3, we have the remainder of 2 in this set. Okay, now there are only 3 equivalence classes for this equivalence relation. And they are mutually disjoint, as you can see. And they are also collectively exhaustive. That means if we take the union, let's write from 0, equivalence class of 0, union equivalence class of 1, union equivalence class of 2. So and that covers the entire set of integers. So therefore, this collection of 3 subsets, bracket 0, bracket 1, and bracket 2. These subsets comprise a partition of integers. Okay, so it's interesting. The set of integers contains infinitely many integers, of course, but we can classify all integers into 3 classes according to the remainder when divided by 3. And there are only three classes, equivalence classes in this case. And this collection is usually written as Z divided by this equivalence relation. Okay, and it's called a quotient set of integers by this congruency in this case. In general, we can define if we have an equivalence relation on set S, and equivalence relation is called tilde, then the partition of S induced by this equivalence relation is written as this, and is called a quotient set. So in short, a quotient set like this one is the set of the collection, or maybe I should say collection, the collection of all equivalence classes by this equivalence relation, tilde. So in fact, we have the following theorem. S by tilde, given that S is a set and tilde is an equivalence relation on the set S, is a partition. Partition of S. So let's try to prove this. So proving this requires to check the 3 conditions of a partition. So first condition is that each element of this collection is non-empty. Okay, so for any x in S, we have x is equivalent to x. Because we're assuming that this is an equivalence relation, so this must hold always. So therefore, x is an element of the equivalence class of x. Of course, it's trivial. Therefore, any element of this collection is non-empty. Is non-empty. So for any this, we have non-empty set. So the first condition is okay. And second condition is that any two elements of this collection are mutually disjoint. Okay. So for any, let's say, y and z, so take any two elements from this collection. Then suppose y is not equal to z. Suppose they're different. And also, the intersection is non-empty. We prove by contradiction, okay? Z is non-empty. Then we can pick, then there exists some x such that x belongs to this intersection. Okay, so from here, therefore, x belongs to, because it belongs to the intersection, x belongs to the equivalence class of y, and x belongs to the equivalence class of z. Okay, so from here, we have x is equivalent to y. And from here, we have x is equivalent to z. And what does this mean? Okay, we can, from symmetry, we can say y is equivalent to x and x is equivalent to z. So by transitivity, so symmetry, because we're assuming this tilde is an equivalence relation, the symmetry holds. And from here and here, we can use the transitivity property. So we have y is equivalent to z, transitivity. So that means the equivalence classes of y and z are actually equal. But this contradicts our assumption that they are not equal. So, therefore, by contradiction, we can say y intersect z is empty. And the third condition is collectively exhaustive, right? And that's actually easy to prove. For any x in S, we have x belongs to the equivalence class of x. And we have shown from the previous condition that x only belongs to one of them, only to this equivalence class. Therefore, x belongs to precisely one of the equivalence classes. Class. So that means, this holds for any element x in S. Therefore, that means S by tilde is collectively exhaustive. And we are done. So in this way, if we have a set and an equivalence class on it, we can always classify all of its elements into equivalence classes. And that's it for this video. See you later.